Hi everybody. So we're going to do a quick problem, and the problem is an open system. It's a diffuser, and we're going to do an Exergy analysis. So basically the problem is, as stated on the screen, steam is decelerated in a diffuser. The second law of efficiency of the diffuser is to be determined. So we're going to assume that the diffuser operates steadily, and that the change in potential energy is negligible. So first of all, we start with the steam going in at 500 kPa and coming out at 200 degrees centigrade. Comes out at 200 kPa as saturated vapor, which means X is 100%. So from that data, we can go into the property tables and pick up values for H, enthalpy, and S. Now down here, because we're talking about saturated steam, that means that we are on the right side of the two-phase envelope, and our value for H will be H sub G at 200 kPa. Our value of S will be S sub G at 200 kPa. So to begin working the problem, let's talk about some of the ideas. The first is, because it's steady, that the rate at which energy enters and the rate which energy goes out will be equal to each other. Also, because there is a single inlet and outlet, M in and M out are equal to each other. So when we set up the energy balance, M dots will cancel out, and we're basically left with H and kinetic energy on each side of the equation. So we rearrange, and we can come out with a difference in kinetic energy. Actual is what we're looking for, and that would be per unit mass. Turns out that the change, this is actually the negative, so the change in kinetic energy actual is going to equal the reverse of this, or 149.5 kilojoules per kilogram. Now that leads us to finding, what we're going to do is we're going to compare the actual to the reversible, or the ideal. So now we're going to do an Exergy balance. Once again, because it's reversible, there is no Exergy destroyed, and because it's steady, there's no change in Exergy in the system. So we can write the equation Exergy in equals Exergy out, both as an extensive and an intensive equation. When we lay out the terms, we find out that the sub-zero terms, which are the dead state terms, cancel each other out, and the equation simplifies to the change in kinetic energy actual is going to equal H1 minus H2 minus T0 times S1 minus S2. Now, as you recall, this is ideal. I'm sorry, I think I said actual. For the actual, we just didn't have this term, did we? In other words, the change was just this. So we can plug in those numbers. T0 is the temperature of the environment, and we come out with a reversible change in kinetic energy of 169.2 kilojoules per kilogram. We can compare that to the actual, which is 149.6, and we get that the second law of thermal efficiency is the actual over the reversible, or 0.884. All right, ladies and gentlemen, well, that is the last vlog for Chapter 8, and I may vlog a little bit later to let you know what's going to happen in terms of the final, but this is the last material that you'll have prior to the end of the course. So we'll talk to you soon.